Hello everyone, I hope you are fine. Uh, my name is Mohammed bin Yunus. I am presenting this conference. The title of our research paper is The Performance Evaluation of Machine Learning Based Techniques via Stator Current and the Stray Flux for Broken Bar Fault in the Induction Motors. The authors of these papers are Mohammed bin Yunus, secondly Najibullah, Assistant Professor Dr. Taner Gupta, Professor Doctor Muslim Arkan, Vigneshwar and Grossmai. In this slide, outline of the presentation is shown. First of all, introduction of the faults in induction machine, specifically broken bar faults are presented. Then the leakage flux monitoring using the flux gate sensor is presented. Then experimental setup, modeling of the induction machine, and the proposed technique, flow chart. After that, feature extraction of current and the leakage flux. Finally, results and the conclusion are presented. Induction machines are widely used because of their rugged construction, low maintenance, self-starting, and simple in nature. Fault detection and condition monitoring remains critical to keep the process uninterruptible. Any impending fault lead to an economic losses, downtime, perturb the maintenance schedule. Broadly, there are two types of the faults, which are electrical and mechanical. In electrical faults, stator faults and the rotor faults are occur. In rotor, the broken bar and end ring fault occurs actually. So in our work, broken bar faults are focused. So from the figure 2, the survey of different organizations has been shown of like in EPRI and IEEE. Uh, from the figure C, the pie chart shows the percentage of different faults in the electric machines. From the figure C we can see that 9% of the rotor faults occur, 25% of the stator faults, 50% of bearing faults are presented in this slide. Here what actually the broken bar fault is described. Following are the root causes for the electric machines, like overheating, frequent start, large load variations, thermomechanical stresses. In manufacturing defects, residual stress and the die casting are the major root causes for the faults. Serious isolation. What happened in broken bar faults? The serious isolation issues that are caused very expensive maintenance, electrical and mechanical asymmetry that increase the stress on the adjacent bar, speed and torque isolation at 2 Fs frequency. So this figure actually shows the asymmetry of broken rotor bar faults. The figure A shows the healthy cases, and the figure B, the highlighted in the black region, shows the broken bar faults in the rotor. Different rotor bar faults detection techniques are presented in literature. Some of them are thermal analysis, chemical analysis, vibration measurement, and electrical analysis. In electrical analysis, current, voltage, back EMF, and the flux are the main components which are usually used for the detection of the faults. In flux, leakage flux contributes greater for the detection of the faults in the broken bar faults. So here some in our work, leakage flux is compared with respect to the stator current for the detection of the rotor broken bar faults. So in the figure 4 present the signatures for the Fs for the stator current in healthy case, and all other like 1 minus 2s into Fs and other signature for the frequency chain of the broken bar faults. Using flux gate sensors for the monitoring of broken bar faults. Different sensors used for the detection of the leakage flux in electrical machine. First of all, Hall effect sensor that need to be installed in the air gap. This sensor also temperature sensitive. The drawback of this sensor is to install in the air gap, which increase the cost and the working. Secondly, the bulky search coil that provides relative value, which is hard to install and its value depends on the number of the turns. Thirdly, the flux gate sensor that is smart sensor. It's low cost, easy to install on the surface of the motor. It gives the accurate value rather than the relative value depending on the number of turns. In our case, flux gate sensor is used for the detection of the leakage flux. The figure on the right side shows the location of the flux gate sensor on the surface of the machine. This slide shows the experimental setup. The experimental setup was developed for the 2.2 kilowatt 50 Hz motors, which is the star connected. In the figure 5, the test by experimental setup shown with the laser alignment, one broken bar fault is also shown, and the data acquisition was carried out for both healthy and the faulty machines. Similarly, Same same motor was modeled in ansys Maxwell 2D with the same size and the geometry of the actual motor. To generate the rotor faults, bulk conductivity of the one rotor bar is reduced, and in the transient solver the simulation is carried out to measure the current and the leakage flux. The figure on the left side of the slide shows the simulated motor of and location of the flux gate sensor. In the table, the parameters of the induction machines are shown. The flowchart shows the proposed technique for the detection of the broken bar faults. First of all, motor is simulated and experimental setup was carried out. Secondly, the leakage flux and current signal are extracted both from the simulation and experimental setup. After that, signal processing is performed in the Matlab for both signals like current and the leakage flux. During this, discrete wavelet transform is used for the feature extraction. Then the machine learning then the extracted features are fed into the Matlab machine learning toolbox to apply the machine learning. Finally, accuracy is checked to get the desired outcome. Um, Feature extraction using discrete wavelet transform. The wavelet transform defines a signal which comprises of frequency component to decompose into the wavelets and is confined by the frequency and the time. The Lubach's wavelet, which defines and characterizes discrete wavelet transform, can also be called family of the wavelets. The dB4 with the sixth level of decomposition is chosen for the current and the stray flux signal. Figure on the right side, which is the current decomposition. First signal is for the original current and rest of the signals are its decomposition. The figure on the left side shows the leakage flux signal and its decomposition. Statistical feature extraction, which are sample features for the stator current and sample features for the stator stray flux. The features obtained from the discrete wavelet transforms are mean, median, max, minimum, uh, range, standard deviation, median and mean, absolute deviation, L1 norm, L2 norm, max norm are the features. Every set of 11 features as S1 to S9 presented in the table which is calculated from the 1500 sample from the current and the leakage flux. The data set of the features then fed into the classification learner to train the classifier used for the machine learning based classification techniques. Results for the classification accuracy with the different classifier for the current and the stray flux, both for the experimental setup and the simulation. 7 out of 23 classifiers highlighted in the bold returns 100% accuracy for the stator current, while 18 out of 23 is accurately predict rotor broken bar fault using the stray flux. Some classifiers like coarse Cannon gives accuracy of 28% and ensemble boosted tree shows 28%, but these classified shows greater accuracy for the leakage flux. From this table, it can be observed that the stray flux provide better accuracy in comparison for the stator current for most of these classification methods. Confusion matrix and receiver operating curve. The classifier accuracies are evaluated using confusion matrix and receiver operating curve. Here in this slide, confusion matrix shows the performance of the corresponding classifier's algorithm while characterizing the region. In confusion matrix, rows shows the true class while column indicates the predicted class. The green boxes indicate the classifiers had performed well and dictate the true class. Confusion matrix for the fine KNN classifiers using the stray flux data is presented here. A confusion matrix represented graphically in the form of receiver operating curve. It sum of the classifier's total success over conceivable threshold, where area under the curve indicate how well the performance of the classification has been carried out. The figure on the right side of receiver operating curve shows shown for the fine KNN performance. Finally, the conclusion: machine learning based techniques is carried out to detect and classify the broken bar faults using the using the stator current and the stray flux data in the induction machines. 10 out of 23 classifiers provides 100% accuracy, while some of them are giving accuracy greater than 90%, uh, while some of that, such as coarse Cannon and ensemble booster tree, shows lower performance for the stator current, but these algorithms shows greater performance for the stray flux. The result shows that stray flux has a better performance than that of stator current for the broken bar faults in the induction machine. Both simulation and experimental results shows that stator flux provide the better diagnostic results than the stator current. The proposed technique is effective for the broken bar faults detection and in industrial application. Finally, these are the references used in this some of the data from in this presentation. Thank you for the listening. This